Hello, it's November 2nd. This is Dr. Stout, and I would like to talk about how serpentinization makes the jade for me, but also may save the world and maybe the origin of life itself. This is sort of a technical supplement. I'm going to be talking about some things outside of my specialty, geology, chemistry, a range of really specialized technical information that is not my usual topic. But I'm really interested in these subjects, obviously, because I like to carve jade, and also because I'm interested in the origin of life and saving the world. So what is serpentinization? So serpentinization is when water comes down from the surface and encounters a batch of iron-containing rocks in the sort of a set of conditions, a decent amount of pressure and a high temperature, but not too high. And then the rock, the iron in the rock becomes oxidized, and the oxygen is coming from the water, and so it releases hydrogen. And so this was in the news recently, where a new drill hole in France that was looking for natural gas actually found hydrogen instead. And so this is very exciting, and it may well be the saving of the world because it is clean hydrogen that doesn't need other forms of energy to produce it. Obviously, there's a little bit of energy in getting it out of the ground in the first place, but other than that, it is the perfect green energy source. When you burn hydrogen, it just combines with oxygen to make water again, so there's no pollution. There's no particulate matter. It is just about the perfect fuel. It has a couple of problems with storage and things like that. It's very, very bulky. But in terms of just a perfect fuel, it's really hard to beat the cleanness of hydrogen. So why am I so interested in serpentinization? It happens really anywhere water can encounter iron, particularly in a silicaceous rock form. And it's mimicking the same kind of actions that happen when life in a marsh or in a deep sea area also has iron encountering water. So microbes in low oxygen or no oxygen environments can actually use iron and combine it in various ways with water as a form of energy. Sometimes this is an abiotic process that releases hydrogen that the bacteria can then use themselves. So it's also a form of food for the bacteria if it's abiotic. But I suspect in many cases it is a biotic mediated process that is changing iron, Fe, to oxidized forms, first Fe2 and then Fe3. So the two forms of ferric and then ferrous iron that have very different looks. And the ferric iron, the Fe2, is red, while ferrous iron becomes Fe3 and is green, and that is what the green in my jade is. So this is a process that is happening really everywhere that there's both water and iron. And the bacteria are using these as energy forms. And the interesting thing is there is competition between abiotic processes and life. Any energy that's just there to be scavenged, life would like to use it, but sometimes it just, things burn on their own without life being involved in oxidizing something or in moving electrons around. So in the deep sea, it turns out, and in marshes and everywhere this is happening, it turns out that under slightly acidic conditions, bacteria can often outproduce the abiotic sources. And then what they'll do is they'll turn Fe2 to Fe3, the part I'm particularly interested in, And in the production of Fe3, the iron becomes less toxic to the bacteria. It becomes less soluble, and it ends up being excreted as a iron oxide. It actually does these really weird things. It makes these long braided strands as the bacteria get rid of the excess iron. So as they're essentially eating iron, their iron poop looks like long threads. And this forms bacterial mats. You might have actually seen this. Sometimes streams in the summertime, as they're running low, will be a little bit acidic, and you'll start to see a sort of red slime forming on the bottom of the stream. That is actually iron oxidizing bacteria making that reddish slime. But in other conditions, that would be green. Now, obviously, in a stream on the surface, you're going to have enough oxygen that it can form other forms of iron oxide than the green one. But the green one happens preferentially under very deep conditions, preferentially at about 18 kbar, which I had to look up. That's about 18,000 times 14 and a half pounds. Is the actual pressure, comparing it to sort of PSI, so pounds per square inch. It would be 18,000 times 14 and a half to give you the total pressure, and happens at about 300 degrees centigrade. So it's at 18 kbar and 300 C. So it's hot, but not incredibly hot. And these are temperatures that life might actually be able to exist. At those pressures, water doesn't boil, so the cells wouldn't burst. And if life is able to outcompete the abiotic factors under these circumstances, it's a very useful form of energy. So there's a ton of energy released in the process of oxidizing iron. It's a very exothermic reaction. And one of the interesting aspects of it is that as the reaction occurs, it releases the heat to more or less the temperature that it needs. And obviously there's different depths where it can find the right temperature, but it makes its own heat, and it releases about 300 degrees worth of heat, and it like to live at about 300 degrees, 300, 350. So if it gets too hot, the process slows down, and if it cools down, the process slows down. So there's an optimal temperature, but it's able to simply because the process exists, the process will expand the region of that optimal temperature by producing its own heat. So it's a really interesting reaction that has similarities to the way bodies work, right? So that bodies are working at a particular temperature at which they work best to produce that particular temperature. It's a homeostasis. And there is also a changing from one thing to another, changing the iron into the iron 3 and changing, taking the oxygen out of the water and releasing hydrogen. That's metabolism. So there's many aspects of this that really resemble life, and to me are almost a interesting way of thinking about how the Earth is in a certain way alive. And it might actually be life. It might actually be bacteria are helping this process. And one of the sort of interesting side things about this is serpentinization, making serpentine, involves a sort of fibrous, matted look to the resulting minerals, particularly jade. If you look at jade, it looks like almost like felt, like fibers that have been laid down flat and all tangled together, and that's what gives jade its toughness. And if you look at bacterial mats that have been oxidizing iron, as these threads come out of the bacteria, they also form these kinds of matted kinds of felted looks. And I find the similarity somewhat compelling. I mean, obviously, I can't prove anything because they happen to both have these thin matted threads. But it's the kind of thing that is at least, circumstantial evidence that these are bacterially mediated reactions that might be producing the very rocks I carve, which I find very interesting. The matting process produces iron that is pretty resistant. It's insoluble, and so these would make excellent fossils. And one of the ideas about jade is that it's often what's called metasomatic. It's a wonderful word. Meta meaning changing or going beyond, and somatic meaning body. And it's when one rock replaces another rock. And so jade is often seen as being metasomatic. And replacing other things, and it may well have been associated with this kind of iron matting, or a little further out, a little more science fiction-y, the silica in jade and the iron in jade together might be some sort of bacterial or living, let's say, form of production. Archaea are also down there doing some of these things, and there may well be other forms of life similar to life that we know. Not too science fiction-y, but DNA-based life with cells that we don't even know about, right? So archaea were only found in the 70s. Now we're realizing they're everywhere. But there could well be things that are down there that we don't know about at those pressures and those temperatures. Even more science fiction, there might be some sort of thing that's involving transformation of silica itself. Back in the early days of science fiction, that was often one of the speculations, that there was some sort of silica life. I'm not saying there is. Everything I see could easily be done by bacteria, but it's kind of fun to think about that the very beginnings of life may have involved some aspects of silica chemistry. I haven't really talked about that part of it, or why I keep mentioning this at the beginning of life, not just something producing free hydrogen that'll give us clean energy. But the idea is that when this hydrogen is produced, it's often produced both in coastal margins and at seafloor spreading areas and near hydrothermal vents. And when this hydrogen is produced, it's a rich source of food for bacteria. And so chemosynthetic bacteria that are able to eat chemicals as opposed to, say, photosynthetic bacteria that are eating eating light. The chemosynthetic bacteria are using generally assumed to be abiotic produced chemicals such as hydrogen as direct sources of energy. I'm wondering if this hydrogen isn't also being produced by other living organisms, and that would go along with a lot of the way life works. Right, life tends to make its own habitat. Right, life makes soil that plants can grow in. Plants feed the animals, etc. So life makes the habitat for itself. Perhaps the hydrogen that is being produced is actually being produced by bacteria. I think there are some cases where that is definitely the case, and that this hydrogen then provides a ecosystem for a whole wealth of other bacteria and then higher forms of life above that. And so one speculation is that these oases of life may have provided a way for living chemistry to develop in the very early days of Earth. At the very beginning, Earth was not habitable, right, by anything, by any forms of life. And there were, asteroids hitting all the time, comets hitting all the time. It would have been a terrible place for life to evolve. But having a protective blanket of an ocean on top of you would have allowed life to exist in a somewhat more stable environment. The problem is it's not exposed to any sunlight, so there wouldn't be any forms of energy to be used that we normally think of as everything is based on the sun's energy. So it would have to be the chemosynthetic energy. And so one of the leading theories for the beginning of life is that it happened at these underwater sites. Sometimes people say hydrothermal vents, or it could be ocean seafloor spreading areas where it was stable and gave a place for life to develop over time. Another really interesting thing is there's been periodic times when there was the Earth was covered with ice and snow, and there wouldn't have been any place for life to exist on the surface. And during these times, the hydrothermal vent communities and these chemosynthetic vent communities may well have been a way for life to survive during these times when Earth would have not been habitable in any way. There was ice from pole to pole. So it's really interesting to think about how these things are connected. Serpentinization, the formation of serpentine releases naturally hydrogen. It's about somewhere around half a gram per kilo of serpentine of hydrogen that gets produced, and that's a ton, right? So rock is heavy, and for every kilo of it, you're going to get a half gram of hydrogen, which is a tremendous production rate. So this is a very hopeful thing to think about, and it's making jade for me, which is just wonderful. The chemistry is very involved. I definitely do not understand all the aspects of it, but it's really neat to see all the bits that I can understand when I notice something. For example, one of the side chains is making something called magnesite, not magnetite. And I would have thought that magnesite was almost the same thing as magnetite. Magnetite is another oxidized form of iron, perhaps produced by bacteria. There are bacteria that definitely produce magnetite, but magnesite is a magnesium carbonate. And so magnesite, when it forms, is going to be taking CO2 out of the water. So this may be a way that global warming can be addressed as well. That the carbonate rocks may be a way to sequester CO2. So the entire process is wonderfully interesting, and in the news today, and is related to evolution in general, the development of life, the beginning of life. And I thought it would be worth talking about a little bit as sort of a side technical note before we get back to some of my other discussions. Thank you.